So the Kaggle competition is now live. If you need the link, it's offline on the course website. Anyone with a Caltech email address can register for it, which means your friends can also participate if they want to, I guess. But they won't be graded. And you should not work in a team with your friends. We're not in this class. But if someone is just curious and just wants to participate for the heck of it, and they're a Caltech student, they're welcome to just for fun. Some people did that last year. Anyways, and it will run for about 3 weeks. The competition will close Tuesday, February 9th at 2 p.m. And then a write-up of that, just a short description of what you tried, is due a couple days after that. And you could turn that in as a group, as a team. Okay, so today we'll be continuing with our a discussion of ensemble methods, which are just methods that combine a bunch of base models in some way and then make an aggregate prediction in some way. And specifically today, we'll be talking about boosting, which is an ensemble method for reducing bias, and then at the end, a method called ensemble selection. So just to recall, test error. Should be pretty much reviewed for everyone at this point, but just so we go through it together. The goal is to ultimately optimize loss over the true distribution of examples, input-output pairs, which is unknown to us. We have access to a finite data set S, which is denoted S, which is a sample drawn independently from the test distribution. This is what we have to work with. And we train a model which on S, which I'll denote as H sub S. So we draw a new sample, H sub S will be slightly different, that learns to predict the Y given to input X. And the test error, so we do this typically to minimize training error plus some regularization. And then the test error, which we can't actually directly measure, although we can reason about it or try to approximate, is measured as the expected value over the samples from the true distribution, the loss of your trained model on that example. So that is the test error. And overfitting is basically when the test error is much higher than the training error. So you think you're doing quite well with this model that you trained, but in reality, when you apply it on the true test set, you don't do nearly as well. Right. And so the way to think about the training set is there's some test distribution that's unknown to us, and we have a few samples from it that we've collected. This is our training set. And suppose we train a model H that gets most of the training set correct. Then the real test error is if you take this H and you look at all the examples in our test distribution and compute the average loss on our test distribution, that's what we really care about. And so this is the definition of test error. Now if we treat our model that we train as a random variable, so if H is a function of some optimization algorithm that minimizes test error on some test set, and so if the test set is a random variable that we can, that we draw, if we collect another test set, it will look different. Collect another training set will look different. Then you can think of this as the model as a random variable. The randomness is defined by the randomness of the training set we collected. Then the expected test error of the model class. Right? The expected test error of a model class is simply the test error of any model in the model class over the expectation over the randomness of the training examples you collect. Obviously, this is not something that you could directly compute because in practice you're not allowed to draw. You can't actually draw multiple samples of training sets. But this is again a concept that we can think about mathematically. You can think of ways to approximating this using finite data, such as by bootstrapping. We talked a lot last time about optimizing the Bias-Variance decomposition using methods like bagging and random forest. And just a reminder about the Bias-Variance decomposition for squared error, because it's the one that's mathematically most convenient. If we write the expected test, we can write the expected test error of a model class like this, that it decomposes by just standard linear algebra and distributive property and stuff like that, arithmetic, into this. And you can think of this as the variance term. Again, this is specifically for squared error. And the bias term, where the bias term is simply the squared error between some test example, the label, and the average prediction of your model class. Right? And the variance term is the variability of your model class from the average prediction. So the variance term actually does not even depend on the label Y. Right? So this is known as the Bias-Variance decomposition of a model class. And this is just another reminder of Bias-Variance decomposition for a very simple problem of a linear model class. quadratic model class, and cubic model class. And you can measure the squared error of the expected squared error of a model on each of the test points, the red points, as the decomposition sum of the bias plus the variance. So the average prediction of the cubic model class tracks the test distribution very well. So the bias is very low, but the variance can be quite high. So some models experience high test error due to high bias. In which case the model class is too simple to make accurate predictions. Some models experience high test error due to high variance, in which case the model class is unstable due to insufficient training data. So the general concept of ensemble methods is to combine multiple learning algorithms or multiple models or multiple hypothesis classes in a way that you get better test error performance. In the last lecture, we talked about bagging and random forests. Today we'll be talking about boosting and ensemble selection. And you can think of ensemble methods as sort of a meta-learning approach, right? We're not really innovating on the base model class. We're not inventing a new variant of SVMs or logistic regression or decision trees or what have you. It's somehow we're innovating how we take any model class and how we combine them in interesting ways to get better than what we would get just using a single model from that model class alone. And the basic idea to do that is you want to create some kind of new training data, right? If you create the new training data, then you could train a model for your base model class on that new training data, and then somehow you combine the results of the base models, typically by some sort of weighted average of their predictions. What bagging does, as we saw last lecture, is to create new training sets via bootstrapping, and then combines by just simply doing a uniform averaging over the predictions of the trained models over the bootstrapped training sets. Why do ensemble methods work? Well, one way to think about why they work is that they optimize for the bias-variance trade-off in interesting ways. Right? What bagging does is it reduces the variance of low-bias models. Right? Low-bias models, or high-variance models, if you will, are very complex and unstable, like a really deep decision tree, for example. If you just draw a new training sample and you just change the training set by not that much, you can learn a very different tree. Bagging averages them together to create a stable average classifier that reduces the variance while not compromising that much on bias. Today we'll be talking mostly about boosting, which reduces the bias of low variance models. Low variance models are models with model classes that are very, very simple, and therefore they have high bias. Like even the best model in this model class can't really perform that well on your training set. However, what boosting does is it trains a sequence of these simple models and then averages together to form a complex model. Right? So boosting reduces the bias of low variance models. Yeah.
So it seems like we use bagging to reduce the variance and boosting to reduce the bias. Why not just bag and boost together?
Why not just bag and boost together? Yes, people do bags of boosted trees. Right. Let me think about your question for a second. Why not do why isn't that the default behavior to just do both together? There must be a reason because it's not very popular to do both together. Usually
Doesn't it lead to overfitting? Like, doesn't it add to the 3C dimension?
It's not clear to me that that happens often or always. It's certainly not all. I certainly can't imagine that.
So you're using your data set over and over, right?
Yeah. So bagging there's a limit to how much bagging can give you because because the bag samples are correlated with each other, right? And so bagging works within reason. Yeah, I guess it's just not very popular in practice. I'm not exactly sure why. I guess when people try to combine both, you don't get much benefit. I'll have to think about it, try to understand exactly why. But people usually don't do both in practice, one or the other. Some people do. I don't think they get much benefit. Okay, so boosting, also sort of known as the strength of weak classifiers. So some terminology. Boosting was primarily designed to be to use shallow decision trees as their base model class. A shallow decision tree is simply a decision tree with low depth. So in other words, very few nodes, right? Shallow decision, and in the extreme case, they're called decision stumps, which is a tree with exactly one split. And in fact, the early work on boosting focused exclusively on this decision stumps as the base model class. What are decision stumps? Well, they're essentially just linear models on one feature, right? They're just linear models on one feature. Right? So this is a very high bias, low variance model class. Different training sets, if you were to sample different training sets from the test distribution, will basically lead to very similar trees. Right? And the error is pretty high, often barely better than random guessing. So, they're stable, tend to more or less learn the same model, even if you have random repeated samples from the training set. It's therefore low variance, right, over the randomness of the training set. Just a cartoon example, if I drew a training set from the test distribution, it looked like this. A decision stump is basically a linear model over one feature, exactly one feature, and it would train this model, right? Negatives split over positives. If I drew a slightly different sample from the test distribution, so I basically just shifted things around a little bit, you'll learn almost the exact same model. If I drew another sample from the test distribution and trained a decision stump, you would learn almost the exact same model. So boosting works on what's known as weak learners in the literature. So in order to think, a little bit more terminology, let's define the error rate of a model over any distribution, could be test, could be training, some distribution of data points as simply the accuracy, right? The error rate, 1 minus the accuracy. A weak classifier is simply a one whose error rate is slightly better than 50%. So 0.4 or 0.45. Right. A weak learner is basically an algorithm combined with a model class that learns a weak classifier. So shallow decision trees are weak classifiers. The top-down induction to find a shallow decision tree is a weak learner. So the name boosting comes from the question: how do you boost the performance of weak models by combining them in interesting ways? So again, here is the bias-variance decomposition for squared loss. And so we know that the variance term is quite low, right? Weak models have high variance and low variance. And so bagging wouldn't work, right? If we were to do bagging over decision stumps, it would not give us any benefit. It would basically give us no benefit over not doing bagging at all, because if I take the average of these, I can just replace that with just a single one of these and get the same as the average, basically, for all intents and purposes. Right. So bagging doesn't work, right? Because bagging reduces variance, not bias, and our base model classes are already high bias, low variance, right? So there's no point in trying to use bagging here. Okay. So let's try a simple boosting algorithm. And we're going to do one-dimensional regression. So there's a single input feature, which I call x, and then a single output regression label, so real value label. And this is basically just y equals x squared. So this is my training set. And so we learn a decision stump, which basically is a single split over the x input. And then within each split, you predict the mean of the training data that falls into the two child limits. Okay, so if I were to predict a single split, the best single split, right, over this training data, it would split it here. And I would predict the mean over the training data in this split and the mean over the training data in this split, right? Okay, obviously this is not a very good model, right? It learned something better than random guessing, but it's still not very good, right? And y2 here, y sub, so I'm going to do a little bit of notation. Y sub t is known as the residual after the tth iteration of training of models. So I'm going to iteratively keep training weak classifiers and adding them together. So at iteration 2, this is the residual, right? this is the deviation from the correct prediction of my first model. So the label for this example is 0, and my model predicted 6, and the residual is minus 6. If we want to add another model to the first model and take their combined predictions as our ensemble, what we need to do is correct for these residuals, right? Train a model to correct for these residuals. So that's what we're going to do. Our second model, H sub 2, is going to train on the residuals of H sub 1. So it's because our ultimate goal is to add them together. Therefore, if we want to add an H2 to H1 while keeping H1 fixed, not going back to it, then basically the best we can hope for is to try to correct for its mistakes. And so we train on its residual. And this is the residual, and we train the model that can minimize squared error over the residual of the training set for just a single stump, and then you get this tree, this split. And so this is the average prediction. This is the aggregate prediction, the sum of the two models. Right? And now it looks a little bit better than just the first model alone, but still not great. And this process continues. Now we have y sub 3, which is the residual of the original label minus the first and the second model summed together. And this is the residual. We train a model, we train a decision step on the residual, and then we add all three together. That's our final model. And this process keeps continuing until some termination condition is met. So pictorially, it might look like this, right? So this is the residual at iteration 1. In iteration 1, we haven't trained any models yet, so the residual is just the original label, right? We train a model, and this is the sum of the models, which is basically just the first model for t equals 1. At t equals 2, this is the regression target, which is the residual of y sub of the original labels minus h sub 1. We train this model, right, with the decision criteria is here. And this is the sum of the two models predicted over the single input feature. Iteration 3, like this. After a while, it starts to slow as you train more and more of these. If you do more and more of these, it starts to slowly look like this. Right. So, what I just described is a method called gradient boosting. And we'll talk about why it's called, what the gradient comes from in a few slides. So we have a finite training set, right? And we train our model. We train a weak classifier, a shallow decision tree, on this training set. We create a new training set where the labels are the residuals from the first tree, right? The deviation, the errors. Train another. This is a short shallow decision tree on the residual training set. And then keep creating new training sets on the residuals and training. So this method is called gradient boosting. Yes?
This wouldn't work for a classification problem, right? Because then you have 0 and 3.
I will get to classification in about 6 slides. Yeah.
Sorry.
This is just for regression, but it's a good question. But yeah, this is just for regression. Mm-hmm. All right, so why is this called gradient boosting? In order to talk about why it's called gradient boosting, let's go back to gradient descent. And let's just think about linear models for a second, and then we'll talk about how this sort of maps onto gradient boosting. So in a linear model, the regression model is simply the linear dot product of your model with the input features, and minimizing squared loss. And so suppose we do axis-aligned gradient descent. What does that mean? That means we do gradient descent, but we only allow for axis-aligned updates, right? So what does that mean? This is the standard gradient descent. Rule. But instead of taking an arbitrary gradient update, we only take an update along one dimension, not all dimensions simultaneously. And how that basically would work in practice is you just take the dimension that has the largest component and you zero out the rest, right? Or sorry, you take a single dimension that has the largest reduction in loss and then you zero out the rest. So in practice, it might look like this. If this is my squared loss sort of heat map, then at this point, the gradient points in this direction, but I take an axis-aligned update. So I only update along one dimension, one axis, one feature, if you will. Similar here, the true gradient points in this direction, but I just take an axis-aligned update. and so on and so forth. This is axis line gradient descent. It still works. I mean, it's obviously not as fast as gradient descent, but it still works. It'll still get you to the optimal solution. Yeah?
In bagging, you said that at each step when we wanted to choose like the split which has the minimum impurity, you said that we go through all features and all data.
That's for decision trees.
Yes.
Yeah.
And we use this idea in order, I mean, instead of going through all the things, we use this gradient descent in order to choose the best impurity or almost best.
Gradient descent, use gradient. How would you choose the threshold? Yeah, I don't. It's not natural to me. I don't see a natural. I mean, you have to do something else. I mean, maybe there's something there, but you have to. But what you just described doesn't work out of the box, because you have to also choose a threshold, right? Not just the direction. In which case you know. Okay, so this is axis line gradient descent. So now, let's not talk about a vector space, right? Let's talk about a function space. What is a function space? Well, in a linear model, we had one axis or one dimension per feature, right? And so we learn a linear model over the input feature space. Ensemble methods, you could think of there being sort of a potentially infinite space of models, and we learn one coefficient per model. Most of those coefficients are 0. But a few of them are non-zero, and our model is the average over those. Our ensemble model is the average over those models that we put non-zero coefficients on, right? So, where ensemble methods are linear in a function space, right? If we imagine some sort of implicit space of functions where each dimension, each axis is a unique, let's say, decision stump, then an ensemble method is simply a linear combination over decision stumps, right? So that's known as a function space. Space of all possible shallow trees, potentially infinite. Most of the coefficients are 0, but our ensemble method places non-zero coefficients on, let's say, a finite number of these. Right, so we live in this infinite, we're optimizing over this infinite dimensional function space where we put non-zero coefficients on just a few functions. And our model is basically a linear combination of the predictions of these functions. So what are some properties of function spaces? It's actually a generalization of vector space. For example, you could think of a linear model. You could think of each of these h's and as just predicting along a single dimension, right? In which case it's not infinite, it's finite, and then it fully reduces back to a linear model, right? You could think if there's d dimensions, you could think of dh's where each h makes a prediction along a single dimension of your input feature. Yeah.
What's the height of each edge?
So you pick a height, and then you define a function space as all possible trees of that height.
So the trees in one space share the same height.
Yeah, you can think of function space like you pick a model class, right? Like all trees of depth 1, or all trees of depth 2, or all trees of depth 3, and the function space is basically an implicit geometric representation of your model class. Right, where you have one dimension in your geometric representation per model in your model class. There are other ways of viewing it, but this is one way to view a function space. Sort of just a geometric reinterpretation of a model class. Fully generalizes vector spaces, closed under addition, closed under scalar multiplication, and well, with these types of properties, you can think about how do you do gradient descent in function space. Okay, so the function space of weak models, every axis, quote unquote, in this function space is a weak model, a decision stump, if you will. The complex models that we're training are linear combinations of weak models, right? This is equivalent to some point in our function space, right? As defined by our coefficients. So we think of this very simple case as just two functions, right? Who has some error, and as you scale up that function, you get some error. Then the axis line gradient descent is basically combining two different functions while making an update along one function at a time. the coefficient of one function at a time. So here's the ideal functional gradient descent. We start with, a model doesn't predict anything, and then we want to take we want to take an update in our functions, in our ensemble function, in the direction of steepest descent of our loss function in our function space. Right? We want to find a single function that makes the direction of steepest descent. Right? For squared error, it looks like this. If I take the derivative of squared error, it looks like this. Now, because we're making an axis-aligned update, we want to just only update along a single dimension, which basically means we want to train a single function, right? And so if we do the geometric projection onto just one of the axes, you can show that this basically is equivalent to solving this minimization problem, which is essentially is equivalent to finding the h that minimizes the residual. And this is why this is known as, so this it's called functional gradient descent. The method here is known as gradient boosting. Right? We have a function class of weak classifiers that are low variance, high bias. Individually, each of these functions are quite poor, slightly above random guessing in terms of accuracy. And we want to boost them. And we do so via an interpretation of doing gradient descent in function space. Therefore, it's called gradient boosting. Yeah.
So there's a reason that we use this on weak classifiers, not because it's strictly on weak classifiers, but because the function space will probably grow exponentially, so like we need to work on a relatively...
The reason why you do it on weak classifiers is because you're minimizing bias over a class of low variance models. Or people will tell you different reasons, and many of those reasons are mathematically, or roughly speaking, mathematically equivalent, if you will. But if you think about it, we're basically... you want to sort of somehow balance up a bias-variance trade-off and not overfit too much, right?
Yeah.
Don't underfit, don't overfit, right? And so low bias, low variance, high bias models will underfit, and if we just do some complex combinations of them, then you can get a better model that doesn't overfit that much, right? Assuming you don't sort of go overboard with this. Right. So I mentioned earlier, this strictly generalizes linear vector spaces over in which you can define linear models. Right? A function space is basically axis-aligned unit vectors. So imagine we have a function space of axis-aligned unit vectors. So our model, all the models are just a one in one dimension and zero everywhere else. Right? A weak model is an axis-aligned unit vector. Then a linear model has the same functional form over d-axis-aligned over a space of d-axis-aligned weak functions. Okay, so just as the full version. Oops, it's not supposed to be there. Okay, so we have training set. We train a weak classifier. We have created a new training set on the residual, and we do this because solving the optimization problem of the best function in our function class to minimize the residual is equal to projecting onto an axis-aligned gradient descent, projecting the gradient to an axis-aligned gradient descent in functional gradient descent. And we keep doing this until we decide to terminate, usually by early stopping. And this is called gradient boosting. This is the gradient boosting method. For regression. Yeah?
Is it like guaranteed to like always increase the error as we continue doing this, or could it like oscillate weirdly?
It is, if you have a convex loss function over your function class, over your function space, it's guaranteed to decrease the error. I mean, yes, it's guaranteed to decrease the error. Training error. Training error.
The training, yeah.
And the reason why it does that is because why it's guaranteed to minimize a convex loss function over a linear model class strictly generalizes, like the convex gradient descent over a linear model class is guaranteed to keep decreasing the error, right? What the tools you use to prove that strictly generalized to this, like without modification almost. Okay, just to recap of basic boosting. It's an ensemble method, right? It's the final model you predict is some linear combination over many classifiers. In this case, weak classifiers or weak regression models. The goal is to reduce bias by using low variance models. And gradient boosting is sort of can be interpreted as a gradient descent in an axis-aligned gradient descent in function space. Yeah.
So for the decision steps, the function space we're talking about is still finite dimensional because there's only ND.
Right. So the space of all possible decision sums you would care about. Well, that's not necessarily true, right? Because if you boost on the residual, the residual, it's finite dimensional only because you have a finite training set. So there's only a finite number of splits you care about. But once you, let me think. Once you change the labels, oh no, because the x's don't change. Okay, so yes, it's finite dimensional, yes. Mm-hmm.
Is there a case where you're actually dealing with an infinite dimensional function space for a different model class?
So you can think of the space of decision sums as infinite dimensional, but your learning algorithm would never consider more than a finite subset. And in general, for these types of function space type interpretations, they're all implicitly infinite dimensional, or in general, they're implicitly infinite dimensional, but because you have a finite training set, your learning algorithms will never consider more than a finite subset of this principally infinite dimensional function space. Okay. Yeah.
I'm wondering what is exactly the gradient corresponds to in the functional space. I mean, what is exactly the gradient here? You talk about gradient descent, right? So what is the gradient in the functional space?
Okay. So, so you access a line gradient descent you're okay with for linear models?
Yes.
Okay.
I mean, in the decision tree model, what is gradient? I know in the
Right. So imagine we want to take the direction of steepest descent of this loss function in our function space, right? Which is the space of all decision trees, decision stumps, and we're going to do it in an axis-aligned way. Like each axis is a single decision stump, right? So therefore we're going to make one of those decision stump coefficients non-zero, right? And so what that is basically equivalent to solving this optimization problem. Right. If I were doing linear gradient descent, I would say I want to add a linear model that activates only one dimension that has a maximum reduction in the residual of the of my prediction. You get the same thing, right?
So the gradient is the residual.
Right. The solution to this, the gradient is the solution to this minimization problem, right? Over your class of decision stumps. So yeah, we're not actually doing the whole deriving the gradient in analytical form. We're just making an observation that the gradient is basically equivalent to solving this minimization problem for squared loss. Yeah.
Does it make sense to use this on a different class of regression models, or like with high bias and stuff?
Yeah. I mean, decision